Sorry, I had to leave and rejoin so that it would let me share my screen. Bear with me 1 second.
Yeah.
Okay, can you folks see my screen all right?
Yeah, you are quite visible.
Okay, great. All right, well, I'll just get started then. Thank you very much, everyone, for being here today. It's a pleasure to come speak to you. I work on Qiskit with IBM Quantum. I am a developer advocate. And today we're going to spend the next hour learning Qiskit. I'll just give you a quick caveat to start off with. I don't work in academia. I'm not a professor. I don't have a PhD or anything. My specialism is in code. I come from a software background. So this talk is not really going to touch on any kind of quantum theory at all. Hopefully you've kind of learned a lot already during the rest of this conference, but I will leave some links to other resources. So if there's anything that's kind of more related to quantum theory and you want to go back and learn that in your own time, that shouldn't impact you too much for the content that we're going to cover today. I only have an hour, and Qiskit is a huge software package, so I'm going to be moving pretty quickly through different things. We're going to start quite simple and then get more complex as we go through. Don't worry too much about understanding every little detail that I'm going through. I think it's more important to kind of understand the general concepts of what I'm talking about, and then I will share these slides later as well, so that you folks can kind of get all the information later as well. Okay, so let's get started.
Yeah, should start.
So, what does it mean to solve a problem on a quantum computer? I quite like using this diagram to kind of illustrate the concept, because solving a problem on a quantum computer can sometimes be, you sometimes learn different approaches depending on what kind of forum you're learning things in, and sometimes it can be hard to kind of fit all these things together. But I kind of quite like using this visual because it kind of illustrates the whole process from kind of the highest layer of the stack right down to the hardware. So we start on our very kind of like high level abstraction layer. We have a problem that we want to solve. Maybe we want to sample a Bell state or find the ground state energy of a molecule. That is our problem. And then normally what we need to do is we need to find or develop our own quantum algorithm that is going to address that problem. Then we normally will kind of convert that algorithm into quantum circuits. And then that quantum circuit needs to be compiled for a specific backend so that we can then run that quantum circuit, whether it's on hardware or a simulator, whether it's, trapped ion qubit hardware or superconducting qubit hardware, whatever it is, we need to kind of take our quantum circuits, compile it for that specific backend, and then run it. And that's kind of how the whole process kind of works from top to bottom at a very abstract level. And we can use Qiskit to kind of deal with this process. So to get started, first, everything that what you have to do when you're working with Qiskit, you need to install it. You could do that with pip install Qiskit in whatever Python environment that you prefer. Here I'm using a Jupyter notebook. And then let's talk about the quantum circuits. Let's pretend for a minute we've already kind of, we've found our problem. We know what algorithm we're going to use. That's more kind of like on the theory level of solving that problem. Now we actually need to kind of implement this in code. We want to use quantum circuits for this. Hopefully you're already a bit kind of familiar with the concept of quantum circuits, but how do we actually implement them in Qiskit? So this here is a very nice little snippet, which just gives a very basic kind of display of how to build a quantum circuit in Qiskit. It kind of gives you all, some of the key concepts here. First of all, you have to import whatever the quantum circuit class that we need to use. Then we need to initialize a quantum circuit, which we do by just calling quantum circuit. And the argument that we pass here is how many qubits we want to add to that quantum circuit. So in this case, I just want to add 2 qubits. If I want, I could also add classical bits as an extra argument in this class, but for now, I'm just adding the 2 qubits. And then the things that make our quantum circuits work and that make it do all the cool things is our qubit operations, our gates. So hopefully you know what a Hadamard gate and a CNOT gate is, 2 of the most kind of widely used and most important gates in quantum computing. And you can apply them very easily to your quantum circuit using Qiskit by just calling .h to apply a Hadamard, and you have to specify what qubit you want to apply that Hadamard gate onto. And then if you want to do a multi-qubit gate, like a controlled NOT gate, you call CX in this case, and we want to say what our control qubit is in the first argument, and then our target qubit in the second argument. These are only 2 of the like many gates that you could apply, but all of them pretty much work in the same way. You have your quantum circuit object, and then you call dot, and then the function that is normally named similarly to the gate that you're trying to apply. So if you're trying to add a RZ gate, then you'll do dot RZ and then pass your arguments. I'm not going to go through every single gate that you can possibly use in Qiskit. The best thing for you to do is to go to the Qiskit documentation and have a look at our circuit library. And then you can see all the different types of gates, all the different arguments that you need to pass to apply them. And pretty much everything that you could possibly need is there. It's a pretty extensive library. And then the next step when you're building quantum circuits is you also need to do a measurement and you want to get results out of them. So what we could do is either directly apply a measure gate. Sorry, I think someone has some background noise. I don't know if they can mute themselves. So if you want to measure your qubits, either you can add a measure gate directly, or this handy function here is really useful. If you want to just measure all of your qubits at once, you can just call measure all, and then you don't have to apply a measure gate on every single qubit. And this will automatically add extra classical bits to your circuit. So remember up here, I didn't add any classical bits to my quantum circuit. I only added qubits. And this measure all function will kind of automatically add some classical bits for me to store those results that I'm measuring. And a nice thing about Qiskit is you can just print out your quantum circuit and it will kind of draw it in this kind of text drawer format for you. So you can visualize really quickly what it is that you've actually built. So here we can see I've added my Hadamard gate, I've added my controlled NOT gate, and then I've done the measurement gate, and it's created 2 measurement qubits for me to store those results in. So this is like your bread and butter of Qiskit. This is the kind of very basic kind of concepts of building quantum circuits with Qiskit. Obviously, this is a very small example, but you can make these much more complex. You can use Python for loops and things to kind of iteratively add things to them. And yeah, this kind of forms as like the basic kind of structure of how you would write a program using Qiskit. And if you don't know what a Bell state is, this is the quantum state that I've generated. If you can go to learn.qiskit.org to kind of learn a bit more about the theory around what it was that I just created here. You can also, this is an example of another type of gate that you can add. You can also kind of really easily customize the gates that you're creating for your quantum circuit. So if you want to use very specific rotations that aren't like already kind of available in one of the standard gates, you can use this generic U gate. Here I've just created a quantum circuit and I'm applying this U gate, and this U gate takes 3 different arguments which correspond to the 3 angles that of rotation that you want to apply, and then lastly it takes the qubit that you want to apply that gate to. And then if I print out that gate, it will just print out something like this. So this is if you want to do like a more custom rotation, which is also really helpful when you start doing more kind of complex calculations on your circuits. Next, I want to talk about parameterized circuits. These are really great for variational algorithms. If you don't know what a variational algorithm is, we actually have a brand new course in the Qiskit textbook on variational algorithm design. It only got released like a week ago, so I've just dropped the link in there, and you'll have these slides afterwards. Go check that out if you are kind of new to variational algorithms, or you want to learn how to kind of create them from scratch yourself. Go send that. And there's also, we're taking feedback on the course as well. So yeah, it's a great free resource. And if everything that I'm saying after this slide sounds like gobbledygook to you, go back and learn that course and then come back and read these slides, because I think it will help put things in context for you. Okay, so the basis of variational algorithms is parameterized circuits. So what that means is you have a circuit that you're going to kind of run multiple times, and you want to use different kind of rotations each time. You want to run the same circuit, but each time you run it, you want to use a different angle of rotation on that same circuit. So what you need to do is kind of parameterize that kind of rotation gate. And to do that, we need to create our circuit in a slightly different way than I showed you previously. And we're going to start with, of course, we need to import the things that we need. So in this case, we need this parameter class. And first of all, we're just going to kind of define a parameter that I'm going to call theta. This is just kind of like a placeholder for now. I'll show you in a minute what we're going to do with it. And then we initialize a quantum circuit. In this case, I'm just, for simplicity, just doing a 1-qubit circuit. And then what I'm going to do is create a kind of control, add an Rx rotation to my qubit. So I'm going to add an Rx gate. And I'm going to pass theta, the parameter, the kind of like the empty parameter that I've just created, to that gate. So in the place where I would have normally maybe sent a single number like a pi/2 or some very specific rotation number, I'm kind of just passing this blank parameter here. And I'm saying that I want to apply it on the 0th qubit, the only qubit that I have in my circuit. And if I just print out that quantum circuit, it will kind of show something like this. I have a single qubit circuit with an X rotation gate. And here I'm just passing theta. It's just blank. It's just a placeholder for now. And what this this slightly different way of doing things means that later on, I can now kind of like swap out that theta for different values as I need it. And the way I'm going to do that is with this concept of binding parameters. So here I'm actually just setting the value of my parameter as pi. And then in order to kind of say to my circuit, okay, swap out that theta for the value of pi, what I'm doing is I need to call quantum circuit and then the function bind parameters. And then the argument that I pass to bind parameters is I say what was the name of that parameter that I created was theta, and then what value do I want to pass to it? And our theta value here was pi. And again, this is like a super simple example, but this theta value could, for example, be like an array of a list of values. So I could have like 20 different values that I'm passing to theta, and it will kind of bind those parameters so that each time I run it in my variational algorithm, it will be using a different parameter. So this is a really great kind of way to, only in like a few lines of code, make kind of your quantum circuits kind of iterate through lots of different possible kind of combinations of values. So it kind of optimizes your programming workflow, if you want to put it that way. Okay, next up, I want to talk about dynamic circuits. This might be a concept that you kind of heard around in quantum computing. It's pretty new, something that, well, has always kind of been a goal for quantum computers, and we're only kind of just now starting to really see them become implemented in, like I think some of the IBM quantum devices now support dynamic circuits. And so Qiskit as well has the functionality for you to be able to write programs in a dynamic way. If you don't know what dynamic circuits are, essentially what this allows is for mid-circuit measurements. So you have a quantum circuit, you measure it, and then based on the results of that measurement, you can then adjust the circuit and keep it running. Whereas previously, up until now, you've pretty much just been able to measure it once, and then your qubits decohere, your circuit kind of is no longer usable, and then you have to run a different circuit, run a new circuit again. Whereas dynamic circuits allow you to kind of keep that same circuit kind of alive for longer, and you can continue doing things. And that opens up a lot more possibilities for us to do things that are really common in classical programming, like if-else statements, while loops, for loops, but with quantum circuits. So it's a really exciting kind of newer feature. So here I have my first example is an if-else statement. I'm just, to start off with, created a quantum circuit, added a Hadamard gate and the first measurement. You need to have that first measurement to kind of trigger the dynamic circuit workflow. And then I have this kind of funky piece of logic here. It can be a little bit confusing to kind of understand, but essentially what I'm saying is if I measure the qubit and the result is 1, then I kind of enter this block here. And this block says, okay, I'm going to then reset my qubit to 0 and then add an X gate to it. I'll just like leave that up for a minute for you to just kind of read and digest that. This syntax is a little bit tricky because we are trying to, it's quite hard at a Python abstraction level to kind of create an if-else statement that works for quantum circuits. So that's why we're kind of using this kind of Python with format. And this kind of, we have to create this if test function to be able to kind of enter into that kind of if block. And then lastly, we do a final measurement gate. And then I'm just drawing the circuit out for you. And if we were going to like run this on a simulator or a real device, the results we would get would either be 0-0 with a 50% chance or a 1-1 with a 50% chance. Oh, wait, sorry, that's wrong. Sorry, it would either be 0 with a 50% chance or 1 with a 50% chance. Right, that was a typo. Okay, next up we have a while loop. Again, creating a basic quantum circuit, adding a Hadamard gate, and then measuring it. We have quite similar syntax here. We have this with, and then our quantum circuit, and then our kind of dynamic circuit function. In this case, we want to apply a while loop. And what this kind of block of logic is essentially saying is that we want to keep measuring this this circuit until we get a value of 1. So the first measurement, you can imagine if there's no, if it gets measured as a 0, then we'll enter this while loop. We'll reset it to 0, we'll add another Hadamard, and then we'll measure it again. If this Hadamard also kind of puts it in the 0 state, then again, we'll go through this while loop. If at a certain point we put this H gate on and then we measure it and it's a 1, that breaks the while loop. So the results we would end up getting here would just be 1. We wouldn't ever get any 0s because it's kind of staying in that while loop until we get that 1 value. And then the last thing we have in Qiskit with dynamic circuits, this is a brand new feature. It literally only got released last week in the latest release. And this is the concept of a switch case. Switch cases are really useful tools in many different programming languages. And to use them here, same as before, I've kind of created a quantum circuit with a Hadamard on it, and I've measured it. And then again, with this kind of with syntax, then the quantum circuit, followed by the dynamic circuit function. In this case, it's a switch. I'm kind of entering into this switch case block. And what this is basically saying is like, there could be many different kind of outcomes that are happening from that first measurement. And based on what we measure, I want to kind of do different things. So if I measure a 0, 0, I want to add a Z gate. If I measure a 0, 1 or a 1, 0, then I want to add a C naught gate. And for any other measurement, I can just pass a default case and say, I'm just going to add a header mark on it. One thing to note is because that these functions are also new, we don't really have a good way of knowing how to visualize this in quantum circuits. So that's why you kind of see in all of these examples, we just kind of have like this very obscure block here. And this is kind of quite an interesting time, I think, in quantum computing, because we don't really know. The circuit model has always been a really useful tool for visualizing what things are doing, but we're kind of getting to a stage where it's becoming really complicated, and we kind of have to rely more on understanding the code itself to figure out the logic rather than using these kind of visual aids, at least until we can figure out a nice way to visualize this kind of thing. Okay, so the next thing I want to talk about is the concept of primitives. So now that we've kind of like learned a bit about how to build circuits, the different types of circuits we can build, how do we actually run those circuits and get results with Qiskit? And I'm going to talk to you about primitives specifically, because this is somewhat newer way of running circuits, and it's quite an important kind of step forward for Qiskit as an SDK, and also hardware providers such as IBM Quantum. They've kind of like started to develop this new kind of paradigm for how to run things on quantum computers. The concept of a primitive, just in general programming, is kind of the idea of having like the smallest kind of building blocks that you can to kind of do something useful. So how this works in quantum computing, whether you're on a specific hardware provider or with Qiskit, is there are two basic primitives that are available at the moment. There is an estimator primitive and a sampler primitive. And these are basically meant to be kind of the most foundational things that most users will probably want to do with quantum computing. The estimator primitive basically calculates expectation values for you. This is one of the most kind of common things that people that are running, variational algorithms using quantum computers, what you're generally trying to get is expectation values of observables. The other primitive is a sampler primitive. This is for kind of calculating probabilities or quasi-probabilities of bit strings from quantum circuits. So that's, you can imagine if you run a Bell state and you want to get the probabilities of getting a 0, 0 or 1, 1, like that, you would use a sampler primitive in that case. Yeah, so those are kind of like the two basic concepts. And then we'll kind of see how you can implement them now with Qiskit on a simulator, on kind of a real backend, on different types of backends. That's what we're going to kind of dive into now for the rest of the time. Okay, so starting off with the sampler. As I said, the sampler primitive calculates the probabilities of getting certain bit strings from your circuit. So I'm going to start off very simply with sampling a Bell state. We're going to take the same Bell state that we were running earlier. And to start off with, the first thing I'm going to do is import the sampler from Qiskit.primitives. This sampler here, because it's coming from Qiskit primitives, this is basically selecting a built-in Qiskit simulator to run this circuit. So I need to kind of initialize it. No, I'm not specifying any particular backend for this because it's just a simulator. There is no backend. It's just Qiskit's like built-in simulator. Then I need to run that circuit. So I'm just saying sampler.run, and then I'm passing the circuit that I want to sample. So in this case, I'm using the Bell state that I created earlier on. And then I actually want to get those probabilities out that I created earlier. So once that sampler has finished running, I can call .result.quasi-dists, which is short for quasi probability distribution. And then the first item in this kind of result object is what I need to actually get the results that I want. So in this case, it's printing out the results that I would get from running a Bell state. These are kind of binary values. So this would be if I measured 0, 0, and 3 would be if I measured 1, 1. And you can see kind of as we would expect, 50-50% pretty much. 50% chance of getting a 0, 0, 50% chance of getting a 1, 1. Okay, and then also Qiskit has some really nice visualization tools baked in, so I can visualize the results that I've created by using this plot histogram function that's available from Qiskit.visualization, and just pass in that kind of result data that I got, and then I can spit it out in a nice little histogram. Qiskit, I'm not going to touch on the visualization module too much in this talk, but it is really, really useful if you want to do any kind of nice data visualizations based on the results that you get back from your experiments. So I really recommend going and checking out the documentation for this module. You can, and it's based on Matplotlib, so you need to have Matplotlib already installed. But that means that you can do a lot of like any complex customization that you can do with Matplotlib, you can pretty much do with the tools in this visualization model. So you can change colors, you can add different axes, you can kind of, yeah, if you're good with Matplotlib, then you can use the Qiskit visualization module pretty easily as well. Okay, so now that we've seen how we do it with Qiskit's built-in simulator, let's ramp it up a bit and try it with a real device. For this, what I'm going to need to do is select a particular provider. In this case, I'm going to be using Qiskit IBM Runtime. This is an IBM Quantum provider that gives you access to IBM Quantum backends. And it's called kind of the Qiskit Runtime service is the thing that kind of gives you the access to those devices. And then this runtime also has its own sampler. So this can get a little bit confusing if you have like the same words like sampler and estimator being thrown around by lots of different packages. So it's a good moment to just kind of remember to kind of check which you're getting the right sampler you need from the right package. So in this case, we're using the sampler from Qiskit IBM Runtime. So the first step here is we need to kind of initialize the service itself. So we need to kind of select which kind of backends that we want. We need to kind of access, you need to use your IBM Quantum API token. If you don't have one already, then you need to access it from quantumcomputing.ibm.com. It's free to like log in, create an account, get a token. There's a few devices that are available for free. Obviously, if you want the more kind of if you want more qubits, then you'll need to kind of pay for access to those. But if you just want a small number of qubits, you can access them through the free plan. And then, yeah, so we've kind of initialized our connection to the IBM Quantum service, and then we want to select which backend we want from that service. In this example, I've just selected IBM Perth. That's a specific backend available in the open plan. I can't remember how many qubits it has off the top of my head. And then the next step is initializing the sampler. And this time, what's different from when we did it with the simulator is we actually have to specify which backend we want by passing a backend to this kind of session argument. And then after this step, it's all exactly the same. We do sampler.run, we pass the bell state, we wait for it to run, we get the job results, we get the quasi distributions, and then we print it out. And as you can see here, now instead of just having 2 results because we were running it on a perfect simulator, now we're running it on a real device. So we're getting more results because we have added noise. So we're not just getting results for 0, 0 and 1, 1. We're also getting a small amount of results coming from 0, 1 or 1, 0. And then I can also kind of plot this on my same nice graph here that I used before. This time I'm comparing the results that I got from the simulator versus the real device. Okay, now we're going to move on to the estimator. The estimator primitive basically allows you to compute expectation values. So a good example to kind of demonstrate this, a very classic example, is we're going to estimate the ground state energy of an H2 molecule. So to do that using Qiskit, oh, I'm sorry, it's kind of cut off a little bit at the bottom. Sorry about that. This is obviously a bit more of a complicated example because it's a much bigger problem than just sampling a Bell state. But we need to kind of import all of these things. We'll start with kind of doing this again with the Qiskit's built-in simulator. So we're importing our estimator primitive from Qiskit.primitives. We're initializing our estimator in the exact same way that we did with our sampler, just calling it estimator this time. The next step is we need to be able to create our H2 molecule in kind of code form and in quantum form that we can actually run on a quantum computer. So to do this, don't worry about this too much. If you're kind of understand a lot about variational algorithms, if you've done this kind of thing before, this should kind of make sense. We're using basically a whole bunch of Paulis to kind of represent an H2 operator. And then we need to kind of create our ansatz. Here I'm just using 2 locals because it's a pretty standard one. I'm not doing anything too fancy. And then we also need an optimizer that's going to help kind of with our gradients and things. I'm just using this SLSQP one. There's a bunch of different ansatz and optimizers that you can access in Qiskit. Again, as I said, go check out the documentation. I just unfortunately don't have time to go into all this detail, but there are a lot of things available there depending on the specifics of what kind of problem you're trying to solve. And then we're going to use our classic VQE algorithms, probably one of the most famous variational algorithms that you could have. There's already a very nice class baked into the Qiskit algorithms module that will let you use that. So I'm creating this VQE class. I'm passing my estimator here. That's an important step. Then my ansatz and my optimizer. And then I actually want to kind of compute my minimum eigenvalue. This is going to give us the ground state of that H2 molecule. So I'm saying, okay, I've got this VQE algorithm that I've initialized, and I want to compute the minimum eigenvalue, and I want to use the H2 operator that I created earlier to do that. And then I can print out the results. The result is normally a lot bigger. I just kind of like condensed it down into just the eigenvalue, just the ground state energy that we actually want. It printed out there, but it's cut off. I'm sorry. But yeah, the main concept I'm trying to illustrate here is how to use this estimator, right? You prepare everything you need for your algorithm, and then you pass the estimator to that algorithm class, and then you do your computation. So it's slightly different from the sampler in that we're not doing estimator.run. We have a specific algorithm that we're using, and we're just saying we're telling that algorithm to run itself using this estimator that we've initialized. So how does this look on a real device? So this top part is where the more kind of the difference comes in. And again, it's very similar to how we did with the sampler. Instead of getting our estimator from Qiskit, we're getting it from Qiskit IBM runtime. We need to initialize the service. We need to connect it to with our API token. We need to get ourselves access to that quantum backend. We are specifying which device we want to run the experiment on. And then we're initializing the estimator and specifying that the backend we want to run it on. Remember, we didn't do that in the previous step when we were just using the built-in simulator that Qiskit has. And then from there, again, it's exactly the same. So we create the H2 operator, the ansatz, the optimizer, we create our VQE class, and we pass in our estimator. It's just that this time the estimator we're getting doesn't come from Qiskit itself. It's coming from the IBM Quantum Qiskit runtime provider. I didn't end up running this and getting a value because this is because it's a variational algorithm, it takes a lot longer to run. And just bear in mind, if you only have access to the open plan, it will take quite a while to run this. So I didn't print out a result for you. Okay, so now you've kind of got like an overview of what the sampler is, what the estimator is, how to run it using Qiskit's built-in simulator, how to run it on IBM Quantum hardware. But what about other hardware providers? Sorry. So at the moment, IBM Quantum is the only hardware provider that uses out of the box the kind of sampler and estimator kind of structure of running experiments. But with Qiskit, you can still use that sampler and estimator way of working, even with backends that don't yet have that baked into to their kind of hardware. And so to do this, what we're going to do here, I'm just using the IonQ provider, for example. So if you want to run your experiment on an IonQ backend, what I'm going to do is use this backend sampler from the Qiskit primitives module. And what this is kind of like a primitives wrapper that's provided by Qiskit that lets you kind of pass any kind of other hardware provider backend to Qiskit, and it kind of wraps it in a sampler for you. So you can still do things in your sampler way, and then the equivalent would be a backend estimator as well if you want to do the estimator. And kind of Qiskit kind of will just kind of handle it all for you. It kind of is clever enough that it will say, oh, this person wants to do things in a primitives-based way, but this backend doesn't yet support primitives. So Qiskit will kind of take on that burden for you of kind of like converting your code into something that is actually runnable on those devices. So to do this with IonQ, for example, the way that you initialize the IonQ provider is like this with the IonQ provider, and then you need your API token for IonQ. You need to fetch your backend. So this one, just for the example, I specified IonQ_QPU. And then I want to initialize my sampler, this time as the backend sampler, rather than just the sampler. And I have to pass the backend that I'm using here. So I'm passing the IonQ backend. So this tells Qiskit, okay, I want a sampler that works on this backend, even though this backend doesn't have its own sampler. So I'm getting Qiskit to create that sampler for me. Then everything is kind of the same as we did before. So we have sampler.run using the same bell state that I was using earlier. And then printing out the results. Again, everything else is exactly the same. So I guess that's the important thing to remember with kind of all these different types of ways of running things. Like Qiskit does a really good job of trying to kind of standardize how you do the main bulk of your code. So all of the important stuff, the logic, the like running of the running of the experiment, the getting the results, that is all the same, regardless of whether you're using Qiskit simulator, a different provider, whatever. The thing that is the different step is this earlier step of like getting access to a certain service and then initializing your sampler or your estimator. That is where you kind of need to pay a bit more attention to what backends you're using. Okay, so that is kind of all I have to say on kind of the core Qiskit itself. That was kind of a very whistle-stop tour through some of just like the basic things that you can do with Qiskit. There's still like so much more that I didn't really have time to touch on. But really, like, I recommend you go look at the tutorials, the documentation, all of that jazz. There's lots of links at the end of this slides. The next thing I just wanted to touch on in the last kind of 5-10 minutes is the Qiskit ecosystem. There is a whole kind of ecosystem that kind of surrounds Qiskit, the core module itself. And we call any of those packages the Qiskit ecosystem. And it basically consists of any projects, tools, libraries from a huge range of different developers within the community, some of whom are in IBM Quantum, some of whom are not. And the goal of the ecosystem kind of framework is to kind of celebrate, support, and kind of help promote the development of different quantum technologies that are built on top of Qiskit. So I like to use this diagram as a way of kind of illustrating the ecosystem itself. So we have Qiskit in the middle here, the core repo. If you look at it on GitHub, it's called Qiskit Terra, at least for the time being. And then surrounding it, you have these different members of the ecosystem. In the main tier, we have kind of some other Qiskit related packages that are also maintained by the IBM Quantum team, but they kind of serve different purposes. So we have the applications modules, including Qiskit Nature, finance, machine learning, optimization. So if you're looking to kind of explore any more kind of specific application-based features, those modules are a really good place to look. We also have Qiskit Experiments and Qiskit Dynamics. That's for kind of a little bit more experimentalist tools. We have Qiskit Air, which is a provider. Anything in green on this diagram is a provider. So it gives you access to either simulators or hardwares. Qiskit Air is kind of a different type of simulator. It's not part of the kind of the core of Qiskit. The core Qiskit simulator is kind of quite a basic simulator. If you want to do more advanced simulations, I recommend having a look at Qiskit Air. It can be a lot more performant if you're trying to do kind of much larger experiments, or if you're trying to kind of, you need more qubits or something than the Qiskit simulator gives you. Qiskit Air is a really good alternative. And then kind of like after this main tier, things kind of get a little bit more kind of Qiskit adjacent. They're not maintained by the core Qiskit teams, but they might be maintained by other IBM teams. Or when we get out to this final kind of community tier, these are kind of not IBM affiliated at all, but they are kind of outside collaborators that we like to work with, or that we think are doing really cool things that we want to kind of support and celebrate. And this community tier is particularly important because anyone who has a project that they have open sourced that uses Qiskit can apply to join the ecosystem. And the kind of projects that make good candidates for this are any projects that are open source and are built using Qiskit itself. So these could be research projects or side projects that are not suitable for integrating directly into Qiskit itself. But, you know, you still want to kind of be part of this ecosystem. Any projects that could be kind of used by the quantum open source community or contributed to that are kind of Qiskit adjacent, they could be good candidates for the ecosystem. So I really recommend that any of you that are doing really cool things with Qiskit, quantum computing, and you want to kind of you want to open source it, or maybe it's already open source and you would like to join the ecosystem, you get some kind of, it gives you kind of like a little bit more like visibility for your project. We have a page on our website where we highlight all of the ecosystem projects. It's just like a nice way to kind of join the Qiskit community, really. I'm just going to give you one example of how to do something with a Qiskit ecosystem project. I'm going to show you how to use Qiskit Nature. This is a really good example of an ecosystem project because it is based on Qiskit. So the example I'm going to show you uses the Qiskit algorithms module, but it also kind of adds an extra layer of kind of like chemistry kind of tools on top that are just kind of so specific to chemistry that it doesn't make sense to have them included in the Qiskit core module itself. So here I've just got a lot of imports from Qiskit Nature. We're going to be using this PySCF driver. You'll need to have PySCF installed to be able to use this. And what I'm going to do in this example is basically very similarly to what we did earlier, estimating the ground state energy of H2. I'm going to do the same thing here using Qiskit Nature, but with a slightly more complex module, H2O. And PySCF is a very popular package in quantum chemistry or computational chemistry. And Qiskit Nature plugs in very nicely to these kind of classical, these classical kind of chemistry packages. So you can leverage PySCF to be able to like to get you some much more complex data about a certain molecule than like you would if you had just used Qiskit by itself. And this time what we're doing is we're creating a problem based on this driver, based on this PySCF data around H2O. And we're going to solve it using a combination of this NumPy minimum eigensolver, which comes from Qiskit, as well as the Jordan-Wigner mapper and the ground state eigensolver, which is coming from Qiskit nature itself. And then to get the result, we call the solver.solve, and then we pass the problem. And the result that you get from here is actually a lot more kind of detailed and complex than you would have gotten from just using Qiskit itself. So even though with Qiskit core, we did manage to find the ground state energy of the molecule, we don't have anywhere near the level of detail that this very specific Qiskit nature package has. So this is a really nice example of a Qiskit ecosystem package that is, it's in the main tier, so it's very well supported by IBM Quantum, but it's specifically for those users that want something very specific in the field of computational chemistry. But it still leverages Qiskit features itself. So it makes sense. It's not part of the core Qiskit, but it's still an important part of the ecosystem. Okay, so that's pretty much it for me. The last piece of information, I'll just keep this up here for the moment. This is, you might want to screenshot this. It has like a bunch of different links for you to kind of keep going with your Qiskit journey, I guess. I hope I gave you just like the tip of the iceberg in this talk today, but we have a ton of different learning resources available, whether it's documentation or YouTube. We have a bunch of different kind of social channels where you can find out what kind of Qiskit and IBM Quantum are getting up to. We have a Slack you can join if you have questions or you want to get more involved in the community. If you want to start contributing to our open source kind of ecosystem, you can, maybe you have a project that you want to have join the ecosystem. We have contributing guidelines if you want to actually start getting involved in writing code for Qiskit itself. Qiskit is open source. We do invite contributions. It can be a little bit of a challenge getting started, but if you are confident with Python and confident with coding, I really encourage you to have a look. And then there's also various different kind of programs you can apply for. You can get, there's a Qiskit developer certification. There's the Qiskit advocate, which is kind of a community of people that have contributed to the community a lot. And so we kind of recognize those people as advocates for Qiskit. And so if you are very active in the Qiskit community, you can apply to become an advocate. Applications open every June or July. And it's like an annual application process. You need to already have that. You need to get the developer certification. You need to kind of prove how you've contributed to the community. And then as part of that program, you can kind of join a community of other kind of really enthusiastic Qiskit developers and users. There's mentorship opportunities, networking opportunities, things like that. If you're a researcher and you want to apply for special access to IBM Quantum devices, we have a researchers program. And yeah, there's some other links there if you ever need support, if you want to read our code of conduct. It's a really important piece of kind of guidance around how to interact with our community in a kind of a safe and empathetic way. Please go read that. Yeah, and lastly, the link at the bottom, if you want these slides, they're available. I put them on my GitHub. So yeah, I guess I'll end there. Happy to take questions if there are any. And thank you very much for listening, everyone.
Thank you, Abby, for the wonderful session. So now we will take questions. The hall is open for questions. Please unmute yourself and ask question.
Moon, I have a small question.
Sure, sir.
Abhi, what is this quantum metal? IBM, this Qiskit metal you mentioned?
Yes, maybe if I can go back a couple of slides. Oh, wait, sorry.
In that pie chart.
Yeah. There we go. Yeah. Yeah, sure. So I will say that there are a lot of things in our ecosystem.
Yeah, Qiskit metal.
Yes. So there's a lot of different packages in our ecosystem. I don't know everything about every package. Qiskit metal, as far as I'm aware, is for kind of doing chip design. So So if you are kind of working closer to hardware, this is a really helpful package if you want to kind of visualize how to build chips, basically. I'm not a hardware developer. I don't really know much more than that, but that's what I believe it is. Yeah.
Yeah. Thank you. Yeah.
So any more question?
Hello, Abby, can you hear me?
Yes.
Oh, thanks. Thanks a lot for this great session. I especially liked when you introduced about the loop, while loop and switch case in the circuit. It was really amazing. Just want to know, like when you are actually, applying it in hardware, like when you are actually doing it on backend, then this code, like how do they translate into some unitary circuits on the real quantum machine when they are emulated?
Yeah. So yeah, it's the circuit itself is the same. Like you're still applying the same unitary gates as you would. What the dynamic circuit while loops and stuff help you to do is, say you have a circuit with whatever gates you want on it, you measure that, then you can keep adding more gates afterwards. So it's like, it's not like adding a new types of gates. It's basically like just allowing you to keep adding more gates even after you've already measured something, which is quite a new thing. Previously, if you would just stick your gates on your circuit, you would measure it, and then you wouldn't be able to get anything else from your circuit once it's already been run. But now you can, once it's kind of you can still maintain that connection. You can still add more gates later, and it still kind of gets compiled in the same way down to the hardware. But you just kind of things don't stop after that first measurement.
Okay. Just one more question. Do you have any idea how to convert a cross operator into unitary circuit gates? I tried to look for a lot, but even in Quora also I didn't find anything related to it.
Sorry, there was a bit of background noise. I didn't quite hear the question.
Can you hear me now?
Yes.
Okay, I just want to know, like, if you are aware of cross operators, they are also like some matrix operators, but they are little different in the sense they can't be directly converted into unitary gates. So actually try to search a lot regarding this in Stack Overflow also, but they also didn't have much information. So if you can just, give any link where can I get more information regarding this? How can I
Sorry,
convert
I
a
don't know
cross
what you
operator?
mean by cross operators. Do you have like an example of a specific one?
It's basically like when you are having a density matrix. Okay. So if you are pre-multiplying it with its dagger notation and then post-multiplying by its normal operator notation.
Okay. So what you might want to do is in Qiskit, there is a quantum info module, which gives you a lot more kind of, rather than doing things in like a circuit-based model, it kind of lets you develop things in terms of operators and state vectors and things like that. So I'm not sure specifically what off the top of my head if you'll be able to find what you need there, but that might be a good place to start looking. You kind of get a lot more control. You can like create very custom operators with the like operator class and the state vector class within the quantum info module. So I would recommend having a look there.
Definitely. Thanks a lot. Thanks a lot.
Someone raised his hand. Please unmute yourself and ask question. Emin, sorry, I can't pronounce his name. Hello. I think by mistake he raised his hand.
Oh, I think I see a couple of questions in the chat. I can also see if I can answer some of them. First question, are there any plans on integrating Qiskit with JAX? So the core Qiskit, no, not as far as I'm aware, but I do know that Qiskit Dynamics, which is a package in this main tier, they do have some functionality you can do with JAX. So yeah, that package is specific for doing dynamics related kind of calculations, and they do use JAX as part of that. So I would recommend having a look at that.
Okay. So if you ask myself, the dynamic circuit, that was very much interesting for me. I should explore that one. And another thing, the estimator part. So few days back, I was checking for some VQE material, and in Pennylen, they are using Qschem library. So same kind of thing they are also using. So I think it is maybe some better. So I will explore this one. So thank you, Abby, for being patient and answering all questions. So it's
There are a
time to
few
move
more
on.
there are a few more in the chat. If there's a few more minutes, I can try and go through some more of them.
Yes, you can do.
Someone asked,
Hello.
there's quite a few coming through. I'm not sure I'll be able to get to all of them, but I'll do my best. Is there a certification course to learn quantum computing using Qiskit?
Someone is trying to ask something.
Oh, okay, yeah, sure. Go ahead.
Yeah, good evening. This is Digambar Padulkar. I am a research scholar in QIQT Technological University, Pune, and I am working in quantum cryptography. So, yeah, I'm working in quantum cryptography, and I want to I want to use the Qiskit, but in Qiskit, what portion should I explore? So which will help me to do something for quantum cryptography.
Honestly, I'm not really sure what you could use Qiskit for specifically for quantum cryptography. If I understand correctly, are you talking about how to make kind of like quantum safe algorithms and things like that? Or what do you mean by quantum cryptography specifically? Like using quantum computers to kind of crack classical cryptography algorithms, or creating cryptographic algorithms that are resistant to quantum attacks? What kind of specifically are you interested in?
Yeah, basically protecting the information from quantum attacks.
Oh, okay. So that would be that. So that is not something that you would use Qiskit for. Qiskit is more for like using quantum computers to solve problems, run experiments. If you want to develop quantum safe cryptography, that kind of field of as far as I'm aware as well. So forgive me, I'm not an expert in this, but as far as I'm aware, that kind of field of research is more about what classical methods can we use to prevent quantum attacks. So there are certain kind of new standards that have been developed, that are kind of more advanced than like RSA, for example, that, are designed to be too complex even for quantum computers to be able to crack. So Qiskit itself, I think, is not going to really kind of, Qiskit is not like, it is not for cybersecurity or cryptography. It's not that kind of package. So yeah, that I think is something, that would probably kind of be like out of the Qiskit realm, at least for the time being.
Okay, thank you.
Yeah, I think our time also it is.
I also had a quick question. May I ask?
Yeah, please make it quick.
Yeah. So I was asking if I had something, if I want to implement in a circuit, feedback-based gate, like I want to measure something, and based on the feedback, I want to prepare something. So let's say there is a 2 times prepare measure scenario. Can I do that using Qiskit? Can I perform that type of experiments using Qiskit? I am preparing something, I'm measuring it, and based on the measurement results, I want to prepare again a different state, depending on that measurement result. Can it be done using Qiskit?
Yeah, so that's the section that I was talking about earlier about dynamic circuits. I don't know the specifics of what you're trying to do, but yes, anything that you can, if you can create a quantum circuit for it, and based on if you got a certain number of zeros and a certain number of ones from a measurement, then yes, you can use dynamic circuits to do that.
Okay, thank you.
Okay, Abhi, I think.
Is there any certification course to learn this quantum computing using Qiskit in some platform?
Yes, at the very end, I think on the last slide, I put a bunch of links. There's a developer certification you can get. So yeah, all of the information in the slides will be available afterwards, and I'll send them through. I think we've kind of run out of time for questions, but if you have any more, there are links here where you can go and kind of hopefully find some more information.
Thank you, ma'am. Thank you very much.
Abhi, thanks a lot. You really helped us quite a bit in educating people. Thanks a lot.
Thank you very much for having me. It was a pleasure. Okay.
So thank you, Abhi, for being patient and answering all these things. So now we should give you a thanks.